14th, everyone. Today we have 2064, minimized maximum of products distributed to any store. You are given an integer n indicating there are n specialty retail stores. There are n product types of varying amounts, which are given as zero-indexed integer array quantities, where quantities I represents the number of products of the ith product type. You need to distribute all products to the retail stores following these rules. A store can only be given at most one product type, but can be given any amount of it. After distribution, each store will have been given some number of products, possibly 0. Let X represent the maximum number of products given to any store. You want X to be as small as possible, i.e., you want to minimize the maximum number of products that are given to any store. Return the minimum possible X. So this problem took me a second to understand. But what it's saying is you have a bunch of different product types and each store can only have one of them, and you want to distribute it such that you keep the maximum low, which I guess was the explanation right there. But it just takes a couple times of reading it. But so you want to find what's the what's when you're going to each store and you say hey, have X have X items from a pile, and you need to get rid of all your items. What's a way that you can do that such that it abides by those rules and X is as small as possible? So at first I was trying to think of a formula to do that, but it just did not seem intuitive. For example, if we have, worst case scenario, we have the same number of stores as we have item types, because then you just had to give every store one product type. Now there can't be more product types than there are stores, otherwise this would be impossible, so that's one of the constraints. But you can't have more, but if the worst case scenario, you have equal number of stores to product types, because then whatever the product type is that has the most, that's your answer. Because if there's, if you have 1, 1, 1, 20 and you have 4 stores, you have to give one of the stores that 20 because the other 3 stores have their own product type. Now, say that you had 5 stores, you could chop that in half. You could say, okay, well, 3 stores get the ones, but then now we have 2 stores that can divvy up this 20. So now we have 2 stores with 10. So that started to make sense, and I was thinking maybe it was figuring out a formula to solve for that. But then I thought, well, would you always want to divide in half? Or would you want to divide, what if you wanted to divide into 3? Say you had something like 4, 9, 1, 1, 1, and you had 7 stores. If you divided the 9 in half, then one of the stores will get 5. But if you divide it into 3, then every store gets 3, and then the maximum is that 4 from earlier. So that really threw a wrench into my gears. And I was thinking, well, maybe I could just try out, figure out a solution to figure out how much to distribute each thing by, but it just wasn't working. Then I looked at the topics, and it said binary search. And it made total sense. Binary search is almost saying, don't try to figure out the solution, just test out different things until you find the solution. Don't try to figure out how to actually get the solution. So now it's just a matter of how to do the binary search. So the binary search would then be just test out an X value and see if it works. If it doesn't work, then X needs to be bigger. You need to give more items to each store. So how does that work? Here we go. Here's my solution, and I will explain how to make it better. So we derive M, or we get M for like the product description, or like the problem description. And we have this binary search, and we're going to binary search between these two values, 1 and max quantities. Because remember, the worst case scenario is there's an equal number of product types to stores, because then you have to give each store like a full product type. You can't divide it, so you just get the maximum between those two. And you had to give at least, well, you can't give a store 0 items and expect to get anywhere, because with these constraints, there's going to be at least 1 item. So here we go. I didn't actually use it as a parameter. Instead, I just decided to assign x as a global variable and then use it in this helper function. But this is where my program gets clunky, but it's also kind of intuitive. So it's a good way to explain it, but then not the best way of doing it. For that, I'm going to use someone else's solution. So we have the binary search right here. And this just says, okay, we'll go between the minimum and the maximum, split the difference. And then if it's big enough, then try to lower x. But you have to include the current x in your maximum. Because remember, this could be the lowest that we could go. So we still need, at the end of it, once we've whittled down, we don't want to rule out what could have been our only possible solution. Or our best solution. But meanwhile, if it needs to be higher, then you can rule that out. So now you can say the minimum is x plus 1, because you know that it wasn't the x that you were looking at wasn't a valid x. Haven't we all been there? Am I right? Hey. Okay. So here's the magic of it, and where this program actually, like where this problem comes into play. What I did, at first I had this just be a copy of quantities, but then I tried out having it be zeros and then building it up. A little bit less intuitive, and also didn't speed up the process at all. Actually, let me go towards that one, because that was pretty intuitive. Okay, we'll go to that. So, in this one, we make a deep copy of quantities. We don't just copy it, because otherwise we'd alter the original array, I'm pretty sure. And we have a pointer. And what we're doing is we're getting rid of, we go through the number of stores, and for each store we get rid of a chunk of items from a pile. And we remove X items at a time. So we go through each store and we say, okay, you get X items from this pile. And then if we run out of that pile, then we move on to the next pile. And then if we run out of piles, then we stop. And whether or not it's a valid X is whether or not we ran out of piles. So did we successfully exhaust all of the quantities? If we didn't, then we still have items left over and X needs to be bigger. If we did, then we can try for a smaller X. But that's the core of it, is just distributing it. And this is just like manually, just like on paper, distributing it. And then with that function, you just binary search it until you find the right value. And then at the end, you just return the maximum X, because max X will always be big enough because of this line right here. But min X might not be big enough. And in fact, X might not be big enough. So max X is what you return at the end. Now, how do we make this better? Well, this is kind of clunky. You're making a whole new array. You're going through the array in its entirety. You're going through both like n times. It's too much. This solution by Kosiad Sabir. It's this line right here that really works. And I'm going to steal that. Or it's these two lines. I'm going to steal that and explain it, because it took me a second to understand it. Let's see if that works. There we go. And it works. So my solution was 5% runtime. This, I bet, will be at least 50. Yeah, what? I'm a wizard at explaining someone else's code. Here's how this one works. Instead of doing that whole clunky thing with arrays and pointers, it just boils down each pile into the number of stores that are needed, provided you take X away from them. And it does it by saying this. We have the quantity of each pile, and we divide that by X, which would work for a lot of cases. If X is 3 and you have a pile of 6, then it takes 2 stores to distribute that full pile. But if X is 7, you don't want to, but you want to use floor division, because then you're not playing with decimals, which wouldn't be helpful. You could use ceiling division, but it's kind of clunky in my opinion. It's well, it's not clunky, but like, I don't know. This is cleaner. I think that if you can use just the baseline operators, you should. Well, when appropriate. And right here, it really makes sense. So we add X to it. So we say, okay, so it's going to be, we want to round up. So we say plus X minus 1. I'll show you what that means. If we have 4, and we have, if Q equals 4, and like if a quantity equals 4 and X equals 3, it should take 2 stores to distribute this. If we floor divide 4 divided by 3, we'll get 1. So that's, but we need 2 stores. So what do we do instead? We can round up by just adding an X to it, and then we'll get 1 more. So we'd get 7 divided by 3. But now, well, yeah, so that should equal 2. So we add X. But we also want to subtract 1, because say Q was 6, and we add 3, then we'll get 9 divided by 3 is 3. And that's too many. We just want 2. So by adding X minus 1, we're making sure that we go up into the next bracket of the division without going too far. It will always ensure you go into that next chunk of distribution. I hope I explained that well. I feel like I'm just being wordy now. But there we go. So you just sum up for every pile how many stores it takes to... For every pile, you sum up how many stores it takes to distribute that pile, given the value of X. And you see if you have that many stores. And if you do, you return yes. And if you don't, you return no. And you just binary search it. There we go. So, in short, when you have to find a number and you are taking a little while to figure out what the formula is for it, just binary search it and just say, just check if it's the right answer. Don't derive the right answer. Just look around for it. You know? I think everyone's done that in like math class or something, where you forget a step for a solution. So you just use a calculator and you just start like trying out different numbers to see what it takes to get the right number, and you incidentally do a binary search. Yeah. You don't know what the rules are. Someone made up a number. They thought of the number 63 in their head. They tell you guess between 1 and 100. You guess 50 right off the bat. They tell you higher. There you go. Binary search. Nice problem. And thank you once again to Kosiat Sabir.